Welcome to the class. Today we are going to discuss about the theorem, necessary and sufficient condition for a non-empty subset W of a vector space V of F to be a subspace of V is that for alpha comma beta belongs to W and A comma B into scalars belongs to F, if the combination A alpha plus B beta belongs to W. This is the necessary and sufficient condition for a non-empty subset W of a vector space to be a subspace. To prove this theorem, first we have to know about the definition of the subspace. Here we have the definition of the subspace, that V be a vector space over the field capital V, and let W be any non-empty subset of V. Then the non-empty subset W is said to be subspace of V if W itself a vector space over the field F with respect to the operations defined on V of F. They are vector addition and scalar multiplication in capital V. So, the necessary and sufficient condition for a non-empty subset W of a vector space V of F to be a subspace. But actually definition is W itself a vector space. Using this necessary and sufficient condition, we can prove a non-empty subset of a vector space to be a subspace anywhere by using this necessary condition. A alpha plus B beta belongs to W. Coming to the proof that V of F be a vector space and let W be a non-empty subset of V. Now prove W is a subspace of V of F if and only if for A comma B belongs to F and alpha comma beta belongs to W, A alpha plus B beta belongs to W. In this if and only condition, coming to the necessary part, first we suppose that W is a subspace of V of F. By using this supposition W is a subspace of V of F, now we have to prove that the condition A alpha plus B beta belongs to W, but alpha comma beta belongs to W and A comma B belongs to F. To prove this combination belongs to W, let us suppose that any two scalars A comma B belongs to F and two vectors alpha comma beta belongs to W. Then we know that by definition of a vector space, using the scalar multiplication in W, because W is a subspace of V of F, means W itself a vector space. So we can see a scalar multiplication in W. So using the scalar multiplication in W, A into alpha, scalar into vector, A alpha is again a vector in W, and B into beta is also a vector in W. And that implies we can see for the two elements A alpha, B beta belongs to W, the sum also belongs to W because W comma plus is abelian group because it is a subspace. So in the abelian group, under addition by closure property, sum of two elements in W will also be the element of W. This is by closure law in W. Therefore, we proved for all A comma B belongs to F and alpha comma beta belongs to W. The combination A alpha plus B beta belongs to W. This is necessary part. On the other hand, the sufficient part we have to prove by supposing the condition for all A comma B belongs to F and alpha comma beta belongs to W. The combination A alpha plus B beta belongs to W. We now prove W is a subspace of V of F. To prove W is a subspace of V of F, we have to prove W itself a vector space over the field F with respect to the operations defined on V. They are scalar multiplication and vector addition. For this, first we show that W comma plus is abelian. In the definition of vector space, the first step is we have to show that W comma plus is abelian. To prove abelian group, we have to prove 5 conditions. They are closure law, associative law, identity law, inverse, and commutative. Coming to the first law, closure law, Closure law definition says that for any two elements in W, the sum also belongs to W. Let alpha comma beta are the two vectors in W. To prove alpha plus beta is also belongs to W by using the converse assumption, here we are taking 1 comma 1 belongs to F like scalars A comma B. And then we can write 1 into alpha plus 1 into beta belongs to W by using the converse assumption, that is for A comma B belongs to F, alpha comma beta belongs to W implies A alpha plus B beta belongs to W. We can write here for these two scalars A comma B belongs to F and alpha comma beta belongs to W. The combination A alpha plus B beta also belongs to W by assumption. And then we have alpha plus beta is also an element of W. So therefore, plus is closed in W. Associative law. Second law is associative law. For associative law, select three vectors alpha, comma, beta, comma, gamma belongs to W. Where W is the subset of V, we already know that, non-empty subset of V. So all the elements of W are compulsory the elements of V also. So that in capital B, for these three elements, in the vector space B, for these three elements, we have clearly the associative property under addition. That is, alpha plus beta plus gamma is equal to alpha plus beta plus gamma. So, by selecting alpha, beta, gamma belongs to W, we have proved the result, the equality of associativity, alpha plus beta plus gamma is equal to alpha plus beta plus gamma. This is true for all the elements of W. So, the associative law is satisfied in W. Now, the existence of identity in W. The identity property says that for every alpha belongs to W, if there exists an element, some vector belongs to also W, such that the vector plus another vector is equal to the selected vector. So let alpha belongs to W. We have beta also belongs to W from the selection. And we know that F is a field. So 0 is the 0 element under addition in capital F. Corresponding to the assumption of scalars 0, 0 like A, B, we can consider the combination A alpha plus B beta belongs to W in the above equation 1, from the above equation 1. So 0 into alpha is equal to 0 bar by using the basic properties of the vector space. 0 is the scalar in capital F, alpha is the vector in W. Scalar multiplication of a vector is again a vector which can be represented as a 0 vector. 0 bar plus 0 bar belongs to W. Therefore, 0 bar plus 0 bar nothing but 0 bar, which is an element of W from this line. So, and also we can verify that alpha plus 0 bar is equal to 0 bar plus alpha is equal to alpha for all alpha belongs to W. In this part, 0 bar is identity element in W. Inverse law. For each and every element, we have to discuss the inverse property. For each alpha belongs to W, minus alpha also belongs to W such that alpha plus minus alpha is equal to 0 bar. Then minus alpha is represented as the inverse of alpha and vice versa. So that selected element alpha belongs to W. And already we have from the selection beta is also an element of W. And clearly we can consider minus 1, 0 are the two scalars from the capital F because F is a field. Corresponding to the scalars A, B as minus 1, 0, we can take A alpha plus B beta belongs to W again from equation 1 from the converse assumption. Minus 1 into alpha is minus alpha, 0 into beta is 0 bar belongs to W. Minus alpha plus 0 bar is nothing but minus alpha. Alpha is a vector, 0 bar is a vector in W. Already we have proved in identity property, 0 bar is a vector in W, 0 element in W. So, minus alpha plus 0 bar is equal to minus alpha. And minus alpha also belongs to W from this line. We can also observe that alpha plus minus alpha is equal to minus alpha plus alpha is equal to 0 bar, which says that minus alpha is the inverse of alpha under addition. So inverse of each and every element exists in W. To complete the W1, W comma plus is abelian group, the last property we have to say about commutative law. That alpha comma beta are any two vectors in W, then clearly alpha plus beta is equal to beta plus alpha, because W is a non-empty subset of V. So alpha beta are the elements of W implies alpha beta are also the elements of V. And in V, it is clear that alpha plus beta is equal to beta plus alpha. So if we select any two elements in W, then we can take the equality alpha plus beta, beta plus alpha, because of the reason W is a non-empty subset of V. So commutative law is satisfied. Hence, we proved here by using the 5 properties, W comma plus is abelian group. In the vector space definition, the second stage is scalar multiplication. W is closed under scalar multiplication is the condition now we have to prove. For that, let A comma 0 are any two scalars belongs to capital F and alpha is a vector in W. And we have from the above, beta is an element of W, vector of W. And then from 1, for these two scalars and these two vectors, we consider the combination A alpha plus 0 beta belongs to W. A alpha plus 0 into beta is 0 bar by basic properties of vector space. In capital V. So A alpha plus 0 bar belongs to W. That is A alpha belongs to W. So scalar multiplication is satisfied in W. Now, the third stage of the vector space definition is postulates. These four postulates, if these four postulates holds in the subset W of V, then we can complete the proof of the W be a subspace of V of F. Further, select any two scalars A comma V belongs to F and alpha comma beta are any two vectors in W. And we know that W is a subset of V, so that all the elements of W are the elements of V also. And in V, we know that for all vectors alpha, beta and scalars A comma V belongs to F, the four postulates holds clearly. They are A of alpha plus beta is equal to A alpha plus A beta. A plus B of alpha is equal to A alpha plus B alpha. A of B alpha is equal to AB of alpha. And 1 into alpha is equal to alpha. Therefore, using all these four postulates in capital W and scalar multiplication of A vector in capital W and W comma plus is abelian group. Using all these three stages, we can say that the non-empty subset W of a vector space V of F will be a subspace of V of F. Thank you.